topic for waves. Today we're going to discuss traveling wave. We can send a single wave pulse through a rope by moving our hand up and down exactly once, like this. Or we can repeat the motion to produce a continuous traveling wave like this. Note that rope as a whole doesn't go to the right. The rope particles just vibrate up and down locally. We can use a spring instead of rope. We can repeat the motion to produce a continuous traveling wave. Note that spring as a whole doesn't travel to the right. The spring particles just vibrate left and right locally. If we send a wave pulse through the rope, we see that when it reaches the end, it can do work on the mass. Note that in this case, work was done against gravity in the form of an increase in gravitational potential energy of the mass. We can think of the energy being transferred from our hand to the mass via the momentum or kinetic energy of the particle while they vibrate. Now we have a transverse and longitudinal wave. What is the difference between transverse and the longitudinal wave? The rope transferred its wave pulses by vibration which were perpendicular to the direction of the wave velocity. The wave produced by vibration of particle perpendicular to the wave propagation is called transverse wave. In this case, particles vibrate up and down perpendicular to the wave propagation. This kind of wave is called transverse wave. The spring transferred its wave pulses by vibrations which were parallel to the direction of the wave velocity. The wave produced by vibration of particle parallel to the wave propagation is called a longitudinal wave. You can see the red particles vibrating back and forth parallel to the direction of the wave propagation. Categorize a water wave as transverse or as longitudinal. If you have ever been fishing and used a bobber, you should know the answer. Firstly, the wave velocity is to the left, and then secondly, the rubber vibrates up and down. Thus, the water particles vibrate up and down, and that is the transverse wave. Vibration of the particles up and down, perpendicular to the direction of the wave propagation. Nature of sound waves. Consider a speaker cone which is vibrating due to electrical input in the form of music. As the cone pushes outward, it squishes the air molecules together in a process called compression. As the cone retracts, it separates the air molecules in a process called rarefaction. Since the vibration of the air molecules are parallel to the wave velocity, sound is a longitudinal wave. A compression is a region where air molecules closer and the pressure is higher. Rarefaction is a region where particles are far apart and pressure is lower. Let's take a look at microscopic view of sound pulses. Wavefronts are located at compressions where air molecules are closer and the pressure is higher. The rays are drawn from the source outward and show the direction of the wave speed or velocity. And the rays and wavefronts are perpendicular to each other. Crests are positive maximum displacement, and the troughs are negative maximum displacement. Compression is region where particles are closer and the pressure is higher. Rarefaction is a region where particles are far apart and the pressure is lower. Here's an animation of a transverse wave motion created by placing each of the blue particles of the medium in a single harmonic motion. As you watch the animation, note that each particle has the same period, t. Each particle is slightly out of phase. The wave crest appears to be moving left. Consider the snapshot of following identical mass spring system, each of which is oscillating at the same period as a system to the right. Note that they are all out of phase in such a way that they form a wave as you move in the x direction. At each position x, we have a different value of y. The system at x1 and x2 are 1/4 cycle out of phase. So start from x1, let's draw this one, 1/4, 2/4, 3/4, this one is 4/4, and from here to here again 1/4. So the system at x1 and x2 are 1/4 cycle out of phase. Now we see the same system a short time later. T1 from the last slide and T2 at a short time later is a snapshot. Mass at x1 has gone lower, the mass at x2 has gone lower. Which way does it appear the wave is traveling? Left or right? Let's trace the first. Move it down. Let's trace the second one. And we can see it's moving to the right. The distance from the equilibrium position is called displacement. Amplitude is the maximum displacement. The amplitude is just the distance from the crest to the equilibrium position. Wavelength lambda is the distance from crest to crest or trough to trough. The period t is the time it takes wave crest to travel exactly one wavelength. And the period is same for all particles of the medium in traveling waves. Speed at which crest is moving is called wave speed. So wave speed equals to wavelength over period. And the frequency is how many wave crests per second pass a given point, and is measured in cycles per second or hertz. And frequency is equals to 1/period. A spring is moving in simple harmonic motion by the hand as shown. The hand moves through one complete cycle in 0.25 seconds. A metric rule is placed beside wave 4. What is wavelength? And wavelengths can be from the center of the one compression to the adjacent center of one compression, but for simplicity, we may use beginning of the compression to the adjacent beginning of the compression here like this. That is 4.7 centimeter, which is 0.047 meter. What is the period? Period is the time taken for one complete oscillation, which is 0.25 second. What is the wave speed? Wave speed is the wavelength divided by period. That is 0.047 meter divided by 0.25 second, which is 0.19 meter per second. Graph 1 shows the variation with the time t of the displacement d of the traveling wave. Graph 2 shows the variation with the distance x along the same wave of its displacement d. Use the graph to determine the amplitude of the wave motion. For amplitude, we can use any of the graph. It is maximum displacement from the equilibrium position, which is 4 millimeter. That is 0.004 meter. Use the graph to determine the wavelength. Wavelength is length, which is a distance. So graph 1 is a displacement time graph. Graph 2 is a displacement distance graph. So wavelength is distance. So we're going to use displacement distance graph. And wavelength is 2.4 centimeter, which is 0.024 meter. Use the graph to determine the period. Period is the time taken for one oscillation. And period is a time. So we're going to use graph 1, which is displacement time graph. So period is 0.3 second. Use the graph to find the frequency. And period is 0.3. So 1/0.3 gives us 3.3 Hertz. Use a graph to find the wave speed. Wave speed is a wavelength over period. And wavelength is 0.024 meter and time is 0.3 second. So that gives us 0.08 meter per second. Graph 1 shows the variation with the time t of the displacement y of a traveling wave. Graph 2 shows the variation with the distance x along the same wave of its displacement. A. Use a graph to determine the amplitude and wavelength of the wave motion. Amplitude is a maximum displacement from the equilibrium position. We can use any of the graph. And that is 2 millimeter, which is 0.002 meter. Wavelength is a distance traveled, so we're going to use graph 2, which is displacement distance graph. That is 0.3 centimeter. Use the graph to determine the period and frequency. Period is a time taken, so we're going to use graph 1, which is displacement time graph. And period here is from crest to crest. That is 0.25 millisecond, which is 0.00025 divided by 1000. And the frequency is 1 over period, which is 1 over 0.00025, which is 4000 Hertz. Use a graph to determine the wave speed. Wave speed is a wavelength over period, which is 0.003 divided by 0.00025, which is 12 meter per second. Graph 1 shows the variation with the time t of the displacement x of a single particle in a medium carrying a longitudinal wave in x direction. A. Use a graph to determine the period and the frequency of the particle's simple harmonic motion. Graph 1 is displacement time graph, and that gives us the period. And the period is from crest to crest, which is 0.2 second. And the frequency is 1 over period, that is 1 over 0.2 equals to 5 Hertz. Graph 2 shows the variation of the displacement x with distance d from the beginning of the wave at a particular instant in time. Use the graph to determine the wavelength and wave velocity of the longitudinal wave motion. As the graph is a displacement distance graph, that gives us a wavelength, as a wavelength is a distance. That is 16 centimeter, which is 0.16 meter. And wave speed is a wavelength over period, which is 0.16 over 0.2, that is 0.8 meter per second. The equilibrium position of 6 particles in the medium are shown below. Using crosses indicate the actual position of each particle at the instant shown above. So take a look at this graph. This is equilibrium position, and above the equilibrium, a displacement to the right. Below the equilibrium is a displacement to the left. So let's start from 0. At 0, no displacement to the right or left. So that's cross. Okay, now let's move on to 4. At 4, displacement is to the right by 2. To the right, 1, 2, here. Now let's move on to 8. 8 has no displacement, so stays, or we cross. Now let's move on to 12. 12, yeah, this is 12. That is displacement to the left. That is displacement to the left. 1, 2. Cross that. Let's move on. 16. No displacement. So we're going to cross that. Now move on to 20. 20 which is corresponds to here 20. At 20 we have a displacement to the right by 2. So 1, 2 to the right. So now we have a compression and we have a rarefaction. On the diagram label the center of the compression with C and the center of the rarefaction with an R. That's compression, that's the center, and this is rarefaction, and the center is there. We have these two equations. We're going to use them to derive the wave speed equals to frequency times the wavelength. So wave speed equals to wavelength over period, and we can rearrange wavelength equals to 1 hour period, and the 1 hour period is the frequency. That's proven. A traveling wave has a wavelength of 2 centimeter and a speed of 75 meter per second. What is its frequency? We're going to utilize the new formula. Wave speed equals to wavelength times the frequency. But before that, we need to convert 2 centimeter into meter, which is 0.02 meter. So the speed is 75, wavelength equals to 0.02 meter, and frequency is f. So f equals to 3800 hertz.